to pre-calculus honors.
Okay, so logarithmic functions. We talked about exponentials last time. Now logarithms. So let's explore what we're talking about here really. All right, we're going to raise 2 to a series of exponents, right? So if you have 2 to the power of 1, you get 2. If you have 2 to the power of 2, you get 4. 2 to the power of 3 gives you 8. But what if I want to raise 2 to an exponent and get 6? See, like if I go from an exponent of 2 to an exponent of 3, I'm jumping from 4 to 8. Okay? But what if I want to raise it to something and get 6? What should I raise 2 to the power of in order to get 6? What exponent should I raise 2 to in order to get 6? Okay? That's what a logarithm answers. So to answer that question, we need a logarithm. And the question that we pose is in terms of a logarithm, and it's this. So it says log base 2 of 6 is what? When I see this, if I'm walking down the street and I see this on a billboard, okay, what I interpret from that is, oh, 2 to the power of what gives you 6? That's how I mentally interpret that, okay? So 2 to what power or to what exponent is 6? That's how I answer that, okay? And in fact, logarithms are written like this. Okay, this is the, what is this? This is the standard form of a logarithm. And look at what these are called. This is called the base, and this is the exponent, right? So just like this one, 2 to what exponent is 6? So this is the base, this is the exponent, and this is your answer. Okay? So in order to switch from logarithm to exponential form, literally that's what you do. So the way I, would always tell my students is the b comes up and pushes up this y, right? Literally like carries it up, so it's b to the y equals x. So this is how we go back and forth. Just always remember that the logarithm answers the question to what exponent. So this is it. The logarithm is always going to equal the exponent, okay? Because when we're doing a logarithm, we're looking for an exponent. All right, so basic properties of logarithms. And these are properties that you have to know like you know your name. So if it's 3 a.m., you're fast asleep, you get a phone call, you pick up your phone, it's me, and I ask you, what is the logarithm of 1? You need to know, okay? That's what it is. Okay, so because this is the exponent, right? Because this is the exponent, now let's ask ourselves, if you have a base, this base to the power of what will give you 1? So b to the power of what gives you 1? 0. So log b of 1 equals 0. Okay? Because b to the 0 equals 1. So again, okay, so look, b to the power of what is b? 1. Therefore, log base b of b is 1. Okay? Now, b to the power of x, right, is b to the power of x. Okay, reflexive property. So meaning log base b of b to the x is x. Basically, you can think of, these go away and you just have x. And then you have another one. If you have b log b of x, this is x. Okay? All right. So you have to memorize these. You have to know them by heart. Basically, everybody.
Wait, how do you do the last one?
Okay. So what is this here? Right? Let me stop this. If we want to evaluate logarithms, no calculators, what we want to do is, this is the base, okay? So I want this number 16 written as a power with the same base as the logarithm. So I'm going to rewrite this, log base 2, and 16 is going to be written as 2 to the power of something. So what is 16? It's 2 to the power of 4, okay? You want the base of the logarithm and the base of the power to be the same. And now, what happens here? It's like this property. These go away, so your answer is just 4. Okay? That's it. So basically, the question that I'm answering here is 2 to the power of what gives me 16? 2 to the power of what gives me 16, and it's 4. Okay? All right, here. Log base 5. Now here, I want to write this as a power of 5. So 5 to the power of what? Negative 3. Therefore, this is negative 3. Here, log base 3, 3 to the power of half, right? So this is a half, okay? So again, if this is equal to x, then you ask the question, 3 to the power of what gives you root 3? And it's a half, okay? So here, 8 to the power of what? So let's think of it this way. 8 to the power of what gives you 512? 3. So again, 512 is 8 to the power of 3. So this is 3. And in this case, look, these just go away. So your answer is 15.5. Okay? And you should be able to do, all 5 of these in less than a minute. Okay, so a fraction of a second for each. That's how long it should take you. You should not overthink them. It should just be, second nature.
But we also should under.
Sure.
Isn't it a long lesson?
Okay, so common logarithms, basic properties of common logarithms. The most common base for a logarithm is 10. Basically, that's its favorite base, okay? So when you have log 5, let's say, equals x, if you don't have a base there, the default base is 10. Okay, so 10 is its favorite base. So in this case, if it just says log 1, it's like there's a 10 here. Okay, so again, log of 1 is 0, because no matter what the base is, the exponent must be 0 in order for you to get 1. Okay, log of 10 is 1, because remember, there is an imaginary 10 here. So base 10 to the power of what gives you 10? And the answer is 1. Log 10x is x, because remember, there is a 10 here which cancels out. And we never write the base of 10. It's like writing 1x or 5 over 1, okay? And here, same thing, 10 to the power of log x is x, because there is an imaginary 10 there. Okay, so let's evaluate this one. This is log of 10,000, which is 10 to the power of what? 4. It's 10 to the power of 4, right? So what this is asking, the question that this is asking, 10 to what power is 10,000? And what would the answer to that be? 4. So no matter how you look at it, the answer is 4. Okay? Here, what would the answer be? 12, right? 10 log 10 goes away. This is the inverse property. What about this one? Okay, so 10 to what power equals 14? you cannot do this by hand, so you plug it in the calculator. So go ahead and plug it in the calculator. And we're going to go to 3 decimal places always for these. There is a log button on your calculator. So it's 1.1. Okay, so 3 decimal places. 1.146. All right, so for the next one, log of -12, also calculator. 10 to the power of what will give you -12? Nothing. There is no way, right? There is no way 10 to the power of anything will give you -12. It's not possible. So it's no solution. And we'll find out later that this is actually out of the domain for logs.
Is it possible to solve that with
No, because I is the square root of -1. It has nothing to do with logs. Okay. Now, a natural logarithm. Okay. 10 is the favorite base of the log. However, e is the natural base of the log. It's like e and logarithm were soulmates. Okay. And when they're together, it's just natural for them to be together. Log and e just go together. So a logarithm with base e is called a natural logarithm. Okay? In French, it's that's what it is.
I am so good at this.
In short, it's ln. Stands for.
I knew this because I read it in my chemistry book.
Right.
That's how I knew it.
So
Okay.
a natural logarithm is ln. Okay. The French version switches logarithm and natural. So it's ln. This is where it comes from. Now, ln is just the same as log to the base e. Okay? So log to the base e is equal to ln. It's the same as ln. Okay? So whether I say ln or log base e, they're the same thing. Therefore, it has to have the same properties. So whether the base of the log is a 10 or a 5 or an e, got to have the same properties. Meaning, again, ln of 1 is 0, ln of e is 1, because it's log base e of e is 1, ln of e is x, e to the ln is x. Okay? So, without even thinking, this gives you, here for part A, 4.5. ln of -2, no solution. You can never take the logarithm of a negative number. Okay? E to the ln of 4, 4. ln of 7, we plug it in the calculator, and we get, right. Okay? 1.946. Mm-hmm.
Oh, no.
Andrew, you always do this to us. I take full responsibility.
Okay. So, graphs of logarithmic functions. So here are the properties of the graphs. All right. A logarithmic function looks like this. This is logarithmic growth, and this is logarithmic decay. So basically, logarithms are the inverse of exponential functions. All right? What does an exponential function look like? Like 2 to the x. What does 2 to the x look like? Well, it looks like this. Okay? A logarithm looks like this. Do you see how they're inverses? Because they are symmetric along y equals x. Okay? So they're symmetric. Meaning, what happens to domain and range of inverse functions? They flip. For an exponential function, what's the domain? All reals. For the range of an exponential function, the domain is all reals. For an exponential function, the range is 0 to infinity. For the domain of an exponential function, the domain is 0 to infinity. Okay, so they're switched.
Logarithms are inverses of what?
Exponential functions. Okay, whereas an exponential function has a y-intercept, a logarithmic function has an x-intercept. Okay? An exponential function has the x-axis as a asymptote. A logarithmic function has a y-axis as the asymptote. Now, end behavior. This is clear that as x approaches infinity, f of x approaches infinity. For the other case, okay, we say as x approaches 0 from the positive side, the graph goes to negative infinity. So as we approach 0, the graph goes down to negative infinity. Okay? So this is logarithmic growth, and here we have logarithmic decay. Asymptotes are the same. X-intercepts are the same. The domain and range is the same. The only thing that changes is the end behavior.
So
0 plus represents approaching 0 from the positive side of the axis. So approaching 0 this way on the positive side of the x-axis. And as we approach 0, the graph goes up to positive infinity. As we approach positive infinity, the graph goes down to negative infinity. Okay? All right. What we're going to do next is graph them. And this is brand new. I don't believe you guys did graphing last year. Okay. So, first of all, sorry, 1 second.
welcome back.
To graph a logarithmic function, we're going to take advantage of the fact that this is the inverse of an exponential function. Okay? So, what I have here is f of x equals log 2x, which I can rewrite for a minute as y equals log base 2 of x. Now, I'm going to rewrite this in exponential form, right? So it's 2 to the y equals x. Now, for an exponential function, the asymptote is y equals 0. For a logarithmic function, it's x equals 0. So I have an asymptote here, and it's a vertical asymptote. Now, once you rewrite it as 2 to the y equals x, you're going to use this to plot points. Except things are switched. So remember, everything is inverted. We're doing inverses. So when you do your table of values, remember how we always pick x values and we plug them in to get y? We're going to do it the opposite this time. We pick y values, we plug it in to get x. Okay, so it's reversed. Okay, so when y is negative 2, I plug it into here. 2 to the power of negative 2, I get 1 over 4. 2 to the power of negative 1, 2 to the power of 0, and then I have 2 to the 1 is 2, 2 to the 2 is 4. Now when I go to graph, it's the same thing with the new x values and the y values that I've picked. So it's really, it's refreshing, okay? This, like, for once, we do it, you know, the other way. It's really kind of fun. So when x equals 1 over 4, y equals negative 2. Things get kind of close there. When x equals a half, y equals negative 1. When x equals 1, y equals 0. When x equals 2, y equals 1. When x equals 4, y equals 2. And you see how it's looking like a logarithm now. And you can give it the shape. Remember that here it's going to follow the asymptote. But here it's going to go up slowly but surely. Okay? Logarithms go up rather slowly. All right? So the domain is from 0 to positive infinity, and it doesn't touch 0. The range is all reals. There is no y-intercept. So here I have a typo. I have a couple typos here. There is no y-intercept. It should be x-intercept. Right? Yes. And it's x equals 1. So it's 1 comma 0. Here there is another typo. It doesn't make sense to ask end behavior as x approaches negative infinity because it never goes there. So it's supposed to be x approaches 0 plus. Okay? So as x does approach 0 plus, it goes negative infinity. 0 plus means you're approaching 0 on the positive side of the axis, right? So this way. And then as x approaches infinity, we go to infinity. It's continuous on its entire domain of 0 to infinity. That's not too bad at all. So we're going to do one more very, very quickly. We're going to rewrite this. So if this is equal to y, then it's going to be x is equal to 1 over 3 to the power of y. My asymptote, again, is going to be x equals 0. So when y equals negative 2, x equals 9. When y equals negative 1, x equals 3. 1 over 3, 1 over 9. So when x equals 9, y is negative 2. When x equals 3, y is negative 1. When x equals 1, y is 0. When x equals a third, we're at 1. And then up to 2, I have an asymptote here, and this looks like logarithmic decay. Remember what I said last time? We're not playing connect the dots. So you have to follow through with the asymptote and show me that it's decreasing. Again, logarithms decrease rather slowly. Okay? So when we talk about, oh my God, like this is exponentially huge, right? You know, logarithms are much, much slower. Okay, so as far as homework is concerned, we're none. It's supposed to be x-intercept again. And it's x-intercept of 1. So as far as homework is concerned, we're going to look at just this. Okay? So up to 43, and it'll be due on Tuesday. Due Tuesday.
When we do our second homework, we just do all the same.
Yes, the second one I want it to be a continuation of this. All right, guys, have a great